तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome to the lectures in engineering chemistry. This is the series of lectures on atoms and molecules, molecular models and quantum chemistry associated with molecules. This lecture is the 7th in the series of lectures on engineering chemistry. Today we will continue with the hydrogen atom, the solutions of hydrogen atom, but one particular solutions of the hydrogen atom, namely the angular parts of the Schrodinger equation. Let me give you the basic coordinates of mine that I am from the Department of Chemistry, and here is my email address for any contact regarding this program. In today's lecture we will look at the angular solutions. We will study them. We will not solve the angular equation. The objective of this series is not to provide detailed solutions to the Schrodinger equation for the hydrogen atom, but rather to look at the solutions in a meaningful way and also wherever possible to visualize them. The detailed solutions themselves are lectures of a different kind. They are exercises in mathematical physics. We will not do that here like in the last lecture when I gave you the solutions of the radial part. The same way we look at the solutions of the angular part, we try to analyze and identify patterns in them, and wherever possible we shall also try to visualize them. In this process of visualization one gets the clear picture of the atomic orbital. So the content is, for today's lecture, the solution of the angular equation for the Schrodinger equation for the hydrogen atom. We shall look at the range of the electron coordinates in the hydrogen atom. We are studying these solutions using the spherical polar coordinates or theta and phi, and therefore we must know the correct range of the problem as we have looked at for the wave functions. And also we will look at the plots of both the radial functions, radial distribution functions and angular functions. The Schrodinger equation in spherical polar coordinates, let us recall the equation once again. Recall that the Hamiltonian for the Schrodinger equation for the hydrogen atom is given by minus h bar square by 2m with 1 by r square dou by dou r square dou by dou r, which is the radial part, and the angular part of this problem is given by the other term 1 by r square sin theta dou by dou theta sin theta dou by dou theta. This is one of the two angles involved as the coordinates, and the other term is plus 1 by r square sin square theta dou square by dou phi square, and of course you have the potential energy term E square by 4 pi epsilon naught r into 2m by h bar square. This is the Hamiltonian, and if you look at the Hamiltonian, the angular parts are given by the ones that I draw with the box, the 1 by r square sin theta dou by dou theta sin theta dou by dou theta, and the 1 by r square sin square theta dou square by dou phi square. These are the terms which are solved by separating the Schrodinger equation into the radial part and the angular part. Let's go back and look at the slide. When you separate this out into a radial part and an angular part, the corresponding angular equation that one needs to solve is given by the theta phi equation. I shall leave this as an exercise for some of you to do that. The two-dimensional theta phi equation is now written in terms of 1 by sin theta dou by dou theta sin theta dou y by dou theta. Y is the solution that we are looking for. It is a function of theta and phi. In the same spirit as the quantum mechanics that we were trying to explain in the past few lectures, namely when you have more than one variable, that you try to write down the equation in such a way that the wave functions can be separated into functions of individual variables. Here it is now expressed as a radial function and an angular function, and the corresponding angular function is y. So this is the equation that we have to solve, and this beta is the same as the beta that appeared in the radial part in the last lecture. The solutions of this equation are known in mathematics as spherical harmonics. Schrodinger did not solve these equations. These were well known. Schrodinger's formulation was to relate the known solutions to the solution of his equation that he proposed. The spherical harmonics have been known in various forms earlier, almost 100 years or even more than that, from the solutions of Legendre polynomials, Legendre differential equation, and associated Legendre differential equations. So these are not new. The theta phi equation leads to two quantum numbers. You recall that the differential equations that we have tried to solve, in every one instance, the particle in a box, the particle in a two-dimensional box, the harmonic oscillator, the radial functions, the radial equation for the hydrogen atom, all these things with a certain boundary condition lead to quantum numbers as a requirement, and these are what lead to the discretization of the energy. In the same way, the angular equation with the corresponding boundary conditions that theta and phi take certain values lead to two quantum numbers m and l. The value l was described in the previous lecture as taking the values from 0, 1, 2 up to n minus 1, where n is the principal quantum number associated with the radial equation. Now for any given l, the value of m, which is the other quantum number, takes the following values, namely minus l plus 1, minus l plus 2, all the way up to l in steps of an integer. Suppose you look at a solution corresponding to n equal to 1. The corresponding angular equation solution will contain only l equal to 0 up to n minus 1, which is 0 here. Therefore, l equal to 0 is the only possible quantum number for that particular solution. And what are the corresponding m values? M is also from minus l to plus l, corresponds to only 0. Okay. Now extending this argument to the next case, namely a radial solution with n equal to 2, the corresponding angular equation gives you the following possible values for the quantum numbers l and m. L can be 0, 1, 2 up to n minus 1, which in this case is 0 and 1. Now for each value of l, the corresponding value of m is from minus l to plus l. Therefore, for l equal to 0, the only possible value for m is 0. For L equal to 1, the possible values are m equal to minus L to plus L, which means minus 1, 0, plus 1. Please remember that these solutions are not something that you have a freedom of choice. No, they come out as a result of imposing boundary conditions on the problem as required by the nature of the wave functions, that the wave functions must vanish at the boundaries of the problem and so on. Therefore, the quantum numbers are natural as solutions. You might have learned earlier in high school that these are the quantum numbers associated with the hydrogen atom, and every orbital of the hydrogen atom has 3 quantum numbers. The result that you studied earlier comes out of the requirement of solving the Schrodinger equation very rigorously using the mathematics as we know. Therefore, the choice of m's and l's are not arbitrary but subject to the rules that I specified just a few minutes ago. Let's go back and look at the slide. The solutions are therefore for a given value of L and for a given value of m. Now, given a principal quantum number n, it is easy for you to show that for every n there are n square such solutions of y. We will see that in a minute. First of all, because of the quantum numbers involved, let us denote our solutions y in the form of quantum numbers y, L, m, and these are obviously functions of theta and phi, the 2 variables for the angular part of the hydrogen atom. And there are, what I am saying here is that there are n square such solutions. It's easy to see that. What are the functional forms of these YLM? Now, here I am going to give you the final result. I am not going to give you the differential equation, how we solve them, etc. That's, I mean, several lectures if you need in order to do that. So you have to believe me, and you have to believe all the others who solved such differential equations earlier, that these are the functional forms for the solutions y. We can organize them in the form of a table for a given value of n and for various values of m. It so happens that for L equal to 0 and m equal to 0, this function is actually independent of theta and phi. It is nothing but a constant, and this is a normalization constant, as we will see later. It's y 0 0 theta phi is 1 by root 4 pi, independent of theta and phi. For L equal to 1, there are 3 solutions, m equal to 1, 0 and minus 1. And you notice that for L equal to 1, the corresponding values of y are indicated by y 1, 1, y 1, 0, y 1, minus 1. And the solutions involved, there is a minus sign here, square root of 3 by 8 pi, sine theta e to the I phi. You see that this is a function of theta and phi. y10 is square root of 3 by 4 pi cos theta, and this is independent of phi. y1 minus 1 is root 3 by 8 pi, looks exactly like y11 except for the sign difference here, as well as this one more difference, sin theta e to the minus I phi. The y11 was e to the plus I phi. This is a minus I phi. They appear to be complex conjugates of each other with a sign difference. This is the set of solutions corresponding to L equal to 1. No matter what the value of n is, so long as n is greater than 1, if n is 2, L equal to 1 is allowed. If n is 3, L equal to 1 is also allowed. Therefore, no matter what that value of n is, the principal quantum number is, you call as the second orbital or third orbital or fourth orbital. You remember 2s, 3s, 4s, 5s, etc. What are those 2, 3, 4, etc.? They are the numbers n, quantum number n. And no matter what that value of n is, for L equal to 1, these are the 3 possible solutions. For L equal to 2, which is possible only if n is 3, because n minus 1 is the maximum value for L. Therefore, n must be 3 in order for L to be 2. For L to be 2, there are 5 possible solutions, namely m equal to 2, 1, 0, minus 1 and minus 2. And again let us look at the solutions carefully. For m equal to 2, the phi dependence is e to the 2I phi. It is y to 2. The subscript is 2, the superscript is 2 corresponding to m. The superscript here corresponding to m is 1, y21, corresponding to the m value, the exponential here, that the phi function is e to the I phi. y20 does not contain any exponential phi, it is independent of phi. For m equal to minus 1, the phi dependence is e to the minus I phi, e to the minus I phi. For m equal to minus 2, the phi dependence is e to the minus 2I phi. Basically what you see is that whatever is the corresponding value of m, the phi part seems to be e to the Im phi. In fact, that is a rigorous solution that one can obtain by solving the angular part using mathematics. What about the theta dependence? For m equal to 2, the theta dependence y22 is sine square theta. For m equal to 1, there is a minus sine theta cos theta. For m equal to 0, there is 3 cos square theta minus 1. Look at the degree of this, the trigonometric functions here. The degree is 2. This is 2, 2. The maximum here is 2. Sine theta cos theta for y2 minus 1 and y2 minus 2 is sine square theta. So the degree of the theta functions in the trigonometric functions sine and cos for any particular YLM is L, whatever is the value of L. Here L equal to 2, so you have a second degree. What about L equal to 3? L equal to 3 is possible only when you have n equal to 4. And you know, if you remember the periodic table, lithium is 2, sodium is 3s, lithium, sodium and then potassium is 4s. So only when you go to the n equal to 4 case, you can have the L equal to 3 possibilities, and for that there are 7 possible values of m corresponding to 3, 2, 1, 0, minus 1, minus 2 and minus 3. So let us look at these functions again. For m equal to 3, now it should be obvious that the phi or the phi dependence is e to the Im phi. I is square root of minus 1, no problems, we have seen this several times. M equal to 2, e to the 2I phi, m equal to 1, e to the I phi, and so on. Now what about the trigonometric part? For L equal to 3, sine cube theta, degree is 3, sine square theta cos theta, again degree is 3, sine theta 5 cos square theta minus 1, the maximum degree, you see the highest is sine theta cos square theta, degree is 3 again. And so what you see is that for spherical harmonics of order 3L and m, the phi part is, or the phi part is e to the Im phi. The theta part is a corresponding polynomial or a function of sine theta cos theta such that the total degree is L. 5 cos cube theta minus 3 cos theta, the maximum degree here is 3 sine theta cos square theta, sine square theta cos theta. Therefore, there is a pattern that one can easily remember in identifying these spherical harmonics with certain solutions corresponding to L and M. And the last, of course, L equal to 3, M equal to minus 3 is sine cube theta, and there are of course a lot of constants in front of these. You see these seem to be random, they are not actually random, they are obtained by normalizing these solutions. We will see that later. These constants are obtained through basic definitions of how we write the spherical harmonics. Root 35, 105, 21 with minus signs all over the places. You know, that seems to be arbitrary. We don't have to remember any of these, but looking at these functions, one should be able to associate a corresponding L value and M value just by examination, just by visual examination, and that is what I've been trying to do here. Okay. This is what I call as the structure of spherical harmonics. Okay. The whole idea is, of course, the spherical harmonics can be obtained by solving the associated Legendre polynomial and then the 5-part and so on. That is a bit of mathematics. Those of you who are interested in mathematics may refer to special functions sections in differential equations, the solutions. Some of these are listed under orthogonal polynomials known as the Laguerre polynomials, Legendre polynomials, Hermite polynomials, Chebyshev polynomials, Bessel functions and so on. So you can always look at the mathematical details by solving them at your own leisure. But what is important is to understand the structure here of spherical harmonics, namely corresponding L value, M value, and the fact that they can be actually derived by solving the angular equation. These are the things to be kept in mind. So let me summarize that part of the lecture, namely a spherical harmonics with the L equal to 1 has one trigonometric function, either a sine or a cosine term in theta, degree 1. For L equal to 2, the degree of the trigonometric term in theta is 2. For L equal to 3, the degree is 3 and so on. For the 5 part, the solution is exactly e to the I m phi for all values of L and a given value of m. So when m is 0, this is obviously 1, which means it does not appear, and therefore you remember 3 cos square theta minus 1 for L equal to 2, m equal to 0 and so on. Let me give you a little bit about what are the values of these coordinates and how do we do the volume element integration for calculating probabilities, for calculating average values in quantum mechanics, etc. for the hydrogen atom before we move on to visualizing these spherical harmonics. When you plot spherical harmonics in a polar diagram, you will get all the orbitals that you have seen in the textbooks earlier. But before that, let's look at the range of the electron coordinates in the hydrogen atom and keep this in mind in doing all the possible calculations in the next lecture. You recall that for the hydrogen atom, the coordinates that we started off was x, y, z. The Schrodinger equation was written in the x, y, z coordinate system, and then following the conventional wisdom, we transformed this x, y, z coordinate system into the spherical harmonics, the spherical polar coordinate system or theta phi. So the infinitesimal volume, which you need to remember, just as you did in the particle in the 1D box calculation, you remember doing the integrals, integral of sine square x dx and the x ranging from 0 to L, where L is the length of the box, in order to calculate probabilities, in order to calculate average values in quantum mechanics. Same way, if we have to do this for the hydrogen atom, the infinitesimal volume element dx, dy, dz is the volume in the Cartesian coordinate space. And what is the available values for these coordinates for the electron in the hydrogen atom? The whole universe. X is equal to minus infinity to plus infinity, y is equal to minus infinity to plus infinity, and so is z. It's universe. Of course, it doesn't make any sense to have the hydrogen atom nucleus here and the electron sitting in Los Angeles. Okay? It doesn't make any sense. But the probability that such a situation arises and the fact that the electron belongs to the hydrogen atom, the nucleus here, those are all extremely small. Quantum mechanics is going to give you reasonably convincing answers that such probabilities are actually meaningless. Okay? However, in principle, the coordinates allowed for the hydrogen electron with the nucleus at the origin, keeping the nucleus at the origin, the coordinates available to the hydrogen atom electron is the whole universe, minus infinity to plus infinity in all the directions, 3 dimensions, and we talk about a 3-dimensional world. This is the space available for the electron, and therefore how does this translate in the r theta phi coordinate system? The probability of finding the electron somewhere in the universe is obviously, when you add all these probabilities, you put the electron in the universe, it's going to be there only. Therefore, the total probability of finding the electron in the universe has to be 1. So if you write the hydrogen atom wave function as psi, psi star psi dx dy dz as the probability. Let us write this out a little more slowly. If we write psi star x y z psi x y z multiplied by dx dy dz, what is the meaning of this? The meaning of this particular term is that this represents the probability of finding the electron in a volume enclosed between what? Between the range here x to x plus dx, y to y plus dy, and z to z plus dz, that is in the volume range dx dy dz centered around the points x y z. This is the interpretation for the psi. There is no other interpretation for the wave function. I have been telling you, and so have been all my teachers telling me, that the wave function itself is a meaningless quantity. The square of the wave function, the absolute square of the wave function calculated in a certain small region of space gives you the probability of finding the electron in that space. So this quantity is the only meaningful quantity that we can extract by knowing the solutions of psi. But now we write this, instead of x, y, z that I have written here, instead of that we will write this in the form of r theta, that is the psi is now written in terms of psi, r theta and phi, and therefore we need to translate the dx dy dz into dr d theta d phi in that particular space. So let us go back and look at the slide. If you calculate that probability and you add all these probabilities dx dy dz over the entire domain, entire universe, that is the integration, you are adding all these probabilities, then the total probability is of course 1, because the electron, once it is put in, it is in somewhere in the universe. In spherical polar coordinates, of course the dx dy dz has to be written as r square sin theta dr d theta d phi. This again comes from simple volume element calculations using multiple integrals between different coordinate spaces. This is in fact related to what is called the Jacobian of the problem in the transformation between xyz coordinate system to theta phi coordinate system. If you do not know that, this is one thing worth memorizing it. Dx dy dz has to be replaced by r square sin theta dr d theta d phi. What are the ranges of the values? R is of course the radius of the sphere. You recall that it is a spherical polar coordinate system where r represents any given sphere of radius r. Therefore the smallest sphere is the radius, it is a point, the radius equal to 0, and the largest sphere is of course minus or is equal to infinity. So r takes the values between 0 to infinity representing the sphere, and theta, you recall, is the polar coordinate from 0 to pi as it goes from the z axis, the polar axis, the north pole to the south pole, and phi takes you around the globe in a sphere, and that is 0 to 2 pi. This is the limit of integration that one has to keep in mind, just like one has the limits for x, y and z as minus infinity to plus infinity for all three of them. So the limits of integration must be kept in mind in doing these calculations for probabilities and for average values. Now with that we will come to one part of the lecture. Now the second part is, we have looked at the angular parts. Let us see what the angular parts look like in an appropriate coordinate system. Because we are referring to the angular variables theta and phi, we have to represent it in the coordinate system in which theta and phi are obvious. So first we will look at the L equal to 1 case. L equal to 1 is possible only when n equal to 2. That corresponds to this 2. That corresponds to this 2. And L equal to 1 is referred to as P. Remember sharp, principal, diffuse and fundamental, SPDF. the S is for L equal to 0, it is also spherical, but it is always known as the sharp line, and the P is for principal corresponding to L equal to 1. So here when we talk about 2P, we are looking at the N equal to 2, L equal to 1, the corresponding angular parts of the functions. Let us visualize. Now one thing that you have to keep in mind is that the angular part is not the whole wave function. The angular part describes only how the wave function is expressed as a function of two angles. The overall wave function is the angular part multiplied by the radial part, and orbitals are in principle pictorial representations of the overall wave functions, but here we are going to look at only the angular part and we are going to call them as orbitals, but you have to be careful that the shapes and sizes of these orbitals will be different for different p orbitals, namely 2p orbital will have a certain shape, 3p orbital will not have the same shape, because 3p orbital corresponds to n equal to 3, the radial part associated with that is different. So keep that, we have to keep that in mind. We will do the simplest pictorial representation, and also the fact that the angular wave functions are complex, that is there is an exponential im phi in them, I is square root of -1, therefore we are talking about a function which has a real and an imaginary part. So what we have to do is to plot the real parts and the imaginary parts separately, both of which are functions of the real variable theta or phi. So there is no fun in plotting the first function, y is equal to 0, 0, 1 by root 4 pi as a function of theta and phi. It is independent, therefore it is uniformly the same everywhere. But the first interesting function to plot is of course not y11 itself, but the real part and the imaginary parts of y11. You recall e to the I phi sin theta. Let us go back and do the, recall that y11 is proportional to minus sin theta e to the I phi, and y11, y1 minus 1 is again proportional, same constant that you have here in front, but with the plus sin theta e to the minus I phi. Therefore if you know the real and imaginary parts of these functions can be obtained by adding and subtracting these quantities. In this case, because there is a sign difference, the real part is obtained by subtracting one from the other, the imaginary part is obtained by adding one with the other. Let us do this, namely y11 minus 1 plus y11. If you do that, this gives you, leave the constant aside, there is a 1 by root 2 or whatever, there is a 1 by 2, leave that aside. What you have is sin theta e to the minus I phi minus e to the plus I phi. Okay. This is addition because this has a negative sign with the spherical harmonic. This is sin phi. There is a 2, there is a minus I, leave that aside. What I am trying to say is the functional dependence is something like sin theta sin phi. That is by saying this is tilde. You can do the exact algebra arithmetic yourself, but the theta phi dependence is a sin theta sin phi. Now the same thing if you do y11 minus y1 minus 1, y11, you will get something like sin theta cos phi. The cos phi comes because you are adding e to the minus I phi plus e to the I phi. Okay. So what you have is one linear combination gives you sin theta cos phi, the other linear combination gives you sin theta sin phi. I think that should be obvious because if you recall the definition of x, y and z in spherical polar coordinate system, x is r sin theta cos phi, y is r sin theta sin phi, and z is r cos theta. Since we are only taking right now the theta phi dependence, let us limit ourselves to a particular sphere of certain radius r, is a constant, we do not have to worry about this. So you see that sin theta cos phi looks like the x variable, sin theta sin phi looks like the y variable, and cos theta looks like the z variable. Therefore, this particular combination, namely sin theta cos phi, which is the real part of y11, is called the px orbital in relation to the fact that x is like sin theta cos phi. The quantity sin theta sin phi, which is a linear combination of y1 minus 1 and y11, another linear combination, is called py orbital, and cos theta, which is y10, if you remember that did not have any exponential phi dependence because the m value is 0, therefore e to the im phi is 1, m is 0, therefore cos theta is y10, that is like the pz orbital. Okay. So the origin of the terms px, py, pz orbitals basically come from the spherical harmonics, which are exact solutions to the angular part of the hydrogen atom, and the labels x, y and z, which are associated with Cartesian quantities, Cartesian coordinate system, in the spherical polar case lead to linear combinations of these spherical harmonics. Now let us try and plot the pz, and then we will plot the px and the py. Okay. So having kept this in mind, namely y11 is that, and y10 is cos theta, this is like the pz, and this is e to the minus I p sin theta and so on. I have just now said that the linear combination y11 plus y1 minus 1 gives you something like py, y11 minus y1 minus 1 gives you something like px, and let us look at what is the final form, and in this lecture of course I will also show you how to get the final form from the mathematical functions. So this is the px orbital as we have here. How does it look like in all the directions? All the directions, you have got two lobes pointing along the x-axis and the minus x-axis with two different colors. The colors indicate that the function has a negative value on one side of the y-axis and positive value on the other side of the y-axis. We will see this picture a little more vividly in a few minutes. This is just to tell you that the px orbital, as you have seen in your textbooks earlier, comes from rigorous solutions of the hydrogen atom. What about the py? Looks exactly the same as px, except that the lobes, the two lobes, are pointing along the y-axis. Okay. Again, there is a plus minus, there is a positive part, there is a negative part to this. Remember, these are not the wave functions themselves, these are pictorial representations of the angular part of the overall wave function. Okay. A correct representation must involve the angular parts as well, but we call them as orbitals anyway. You have to remember that that is somewhat inaccurate, but it is done for convenience. pz. Again, there is no difference between x, y and z, except that the lobes this time point along the z-axis, positive and negative again. So it looks like there is a symmetry, but you remember the functions do not appear to give any of this. If you look at these, see, one is sin theta cos phi. These functions are very different, sin theta sin phi, and the third is cos theta. And when you plot them in a certain coordinate system, they look exactly the same, except that they seem to be in three different axis systems. The pictures that you saw were plots of these in spherical, in polar coordinate system. It's a polar diagram, it is not a Cartesian diagram. How does a sin theta look like in a Cartesian space? You remember that a sine function looks like that. A cosine function starts from 1 to 0 to minus 1 back to 1. A polar diagram is slightly more subtle. If you plot these functions in a polar diagram, you get exactly those plots. The rest of this lecture is only to illustrate that for these three functions. So let us list these functions and let us see how the polar diagrams are drawn. What we are going to do is only plot the angular part of the hydrogen orbital wave functions. We are going to develop that full plot of the two spheres that you saw from the scratch. Okay. So okay, there are two files here. One is called 2D, meaning it's a two-dimensional picture. The other is a three-dimensional picture. We are going to look at first the function cos phi sin theta. You know, these factors are not relevant right now. It's a real part of y11 cos phi sin theta. The other is imaginary part. Let us look at what is meant by cos phi sin theta in a two-dimensional plot. What is being done here is, since we are plotting a function which is a function of two variables, theta and phi, first let us choose one variable, plot this as a function of that variable by keeping the other variable a constant, and then we will vary that variable. So what you look at here is a plot of sin theta cos phi, okay, by keeping phi as a constant value. Phi is 0 here. You remember that the theta variable is something like a z-axis in a sphere, so that the theta goes from 0 to pi, and if you recall, the phi variable goes around from 0 to 2 pi. Okay. So let us keep the phi at one value, namely along the x-axis, as a constant. Phi is 0, and we are going to plot for phi equal to 0, cos phi is 1, it has the maximum value. Okay. So let us plot sin theta as a function of theta for various values of theta as theta goes from 0 to pi. Okay. Here are the values of sin theta, a few of them. Remember, when you plot a function, you plot a few points and then you draw the line to make it continuous. Okay. So for theta is equal to 0, sin theta is 0, values are given from an Excel spreadsheet. Sin theta is equal to 15, 30, 60, 90, all the way up to 180, all the possible values. So how do you plot this? Okay, how do you plot this is, you mark the value of theta by the radius. Okay, the radius makes the angle theta with respect to this axis. So if you go back, this radius right now makes an angle theta is equal to 0. What is the value of sin theta? You mark that as the length along the radius. Since sin theta is equal to 0, it is right in the beginning, okay, right at the origin. The next is sin theta is equal to 0.25 at theta is equal to 15. Okay, so what you have done here is, this is the angle theta is equal to 15, that's the radius makes with the z-axis, and the value 0.25 is, because you draw a sphere of radius 1, you can mark the length 0.25 as the value sin theta corresponding to theta is equal to 15. What is the next value? You see that for theta is equal to 15, 30, go back and see why that sphere was drawn. You see that sphere, that circle tells you that this is half the value. Since it is the radius, the corresponding half value is here, and that's the point. And then you draw correspondingly all the points for this particular graph for theta is equal to 15, 30, 45, now it is 75, 90, and so on. So we come to the last value, theta is equal to, so now if you join all these points, it looks like a perfect circle. It is a perfect circle. Okay. Now this is for a given value of phi, namely phi is equal to 0. Since you want to plot sin theta cos phi in a polar coordinate system, in which you remember in a sphere, theta is this variable, phi is this variable. Now we have got the theta plot for this variable. Now we have to simulate this for all the values of phi. That is, we have to draw this circle for every value of phi. How do we do this? We have to multiply by cos phi each one of this. Let us do that in the 3 dimension. So what you have here, let me go back to this picture. So the first one is for along the x axis phi is 0. So what you have is the plot sin theta, cos phi is 1. Now as you go from the x axis to the y axis to the minus x to the minus y and back to the x axis, you are going to go from theta phi equal to 0 to 90 to 180 to 217 and then to 360. Therefore you are going to multiply this function by cos phi for every value. When you do that, what do you get? Now that is the plot you will get. Let us go back and see that. You see that the circle shrinks in size because the value of cos phi is less than 1. The circle becomes 0, absolutely vanishing at phi equal to 90 degrees, that is along the y axis, and then for phi greater than 90 cos phi is negative. You see that it keeps increasing but the function is now negative, that is 180, and then it goes down again in value. At 270 it goes to 0, and then it starts increasing again from 270 to 360 because cos phi increases. Now cos phi is positive in the first and the fourth quadrant, therefore the function as a whole is positive here. Whatever the plot that you see here represents a positive part. Whatever you see in this part, the second and the third quadrant, gives you the negative part, and when you draw the continuous plot by keeping all the contours, you see a positive part of the function and a negative part of the function. This is cos phi sin theta. Now it should be obvious immediately to many of you that what is the corresponding plot for sin phi sin theta. Cos phi started with the x axis because the value of phi is 0, cos phi is 1. If we start with sin phi sin theta, the value of phi is 90 degrees corresponding to sin phi equal to 1. Let me close this. Sin phi sin theta, if you look at the corresponding plot, the plot is again sin theta only in 2 dimensions, but we are going to draw this plot for phi equal to 90 degrees because that is where sin phi is maximum. Therefore what you get out of this when you draw, it is again the same plot like what you had, sin theta. Okay? No problems, it is easy to go through the whole and see that the end result is exactly sin theta, except that now it is along the y axis, not along the x axis. Therefore the corresponding 3D plot starts with the maximum along the y axis. This is sin theta along the y axis for phi equal to 90 degrees, sin theta sin phi, and it goes down as phi increases, goes to 0, becomes minus 1 here, goes to 0 and increases. And you remember the value of phi from 0 to 180, sin phi is positive, that is sin is positive in the first and the second quadrant, it is negative in the third and the fourth quadrant. Therefore the function sin phi sin theta looks exactly like the previous one, except that it is rotated by 90 degrees. So it is obvious to see that px and py are 2 orbitals which are identical, except that they are located about, they are centered about, one about the x axis, the other about the y axis. What about the z? That is interesting. It is cos theta, it is not sin theta. Let us look at cos theta. With that we will come to the end of today's lecture. Let us plot cos theta in the polar coordinate system. We have no difficulty with phi because the function is independent of phi, it is cos theta only, that is a z axis. You remember z corresponds to cos theta e to the I m phi for m equal to 0, there is no phi dependence. Cos theta is of course 1 for theta is equal to 0. There is a table which gives you the values up to 180 degrees, cos theta is -1. So let us plot that here. It starts with 1, maximum value theta is equal to 0. Then progressively it decreases, cos theta value decreases. Remember, the length tells you the value, the angle tells you the theta. Okay. So you see the cos theta looks like 2 half circles now instead of 1 whole circle as it was in the case of sin theta. But remember, there are now 2 graphs. There is a red graph and there is a blue graph, because you know that theta, if it is greater than 90, cos theta is negative. Therefore, the function cos theta is positive in the first half of the theta is equal to 0 to 180, that is theta is equal to 0 to 90, and then it is negative, and that is a blue graph. Now, since this is independent of phi, when you plot this in 3 dimensions involving the phi variable, how does it look like? There is no phi dependence, therefore there should not be any change in the shape of this function. It is the same for all values of phi. So there is no problem now. Cos theta leads to an orbital which looks exactly like the px orbital or the py orbital, except that now it is along the z axis. The positive quadrant is because you remember, since it is independent of phi or phi, the theta, cos theta 0 to 90 keeps this as a positive lobe, and theta 91 to 180, this is the negative lobe. So again 2 lobes are there, plus and minus, and the pz orbital looks identical to the px orbital or the py orbital, except that now it is along the z axis. So there is no mystery associated with the p orbitals that you saw earlier. There is no mystery associated with them. When somebody tells you that this is how the orbitals look like, if you understood the last 10-15 minutes of how to plot simple trigonometric functions, which are the results, which are the solutions of the Schrodinger equation for the angular part, you can simply laugh at them, say, well, I understand how to do this. There is no problem in plotting these. These are nothing but polar representations in the 2-dimensional sphere, in the 3-dimensional spherical coordinate system. In the theta phi representation, if you plot trigonometric functions, you get everything that you think about. In the next lecture, I will show the same thing for the d orbitals. You remember that d orbitals correspond to L equal to 2 from your high school chemistry, and the d orbitals are possible only when the principal quantum number n is 3 or more. So that is 3d orbital, 4d orbitals, 5d orbitals are possible, but not 2d. So that when the d orbitals are present, how do we represent the corresponding spherical harmonics? It is exactly by the same procedure that I described here, except that now you have more lobes, multiple points where the functions go to 0 and so on, because the trigonometric functions for the d orbitals are of degree 2. L equal to 2 means that the trigonometric functions contain cos theta and sin theta or sin square theta, degree 2, therefore there is going to be some zeros in between in the functions. In the next lecture we shall do that. Before I conclude this, let me recall that what we tried to do in today's lecture was to look at the solutions of the angular part, examine the solutions, not derive the solutions, and understand what are the possible ranges for the electron coordinates for hydrogen atom in the spherical coordinate system, and also try and understand the spherical harmonics, the simplest of the spherical harmonics, through a graphical representation by first breaking that a variable, two variable problem into a one variable problem, and then extrapolating that into the second dimension and seeing the full three-dimensional structure. There are a few problems which are attached to this lecture until we meet the next lecture, during the next lecture. Thank you very much.